Hello everyone, I would like to present our concept of a trustless, censorship-resilient and scalable voting platform in the permission-based blockchain model. This is myself, Marco Lewandowsky, and Sebastian Gajek from Flensburg University of Applied Sciences. This work was also partly supported by the Horizon 2020 project FinTech. So there's a question, why blockchain-based voting makes sense. Votings in general are an important aspect of nearly every person's life. They are confronted with votings in the small context, like for example when deciding what to eat or what film to watch, but also in grand scale context, for example in elections. So in the classical paper-based voting, which are widely used, are often not suitable for this case because they are considered slow and need a lot of resources. There's a threat of miscounting or even threats of forgeries. But on the other side, governments and private organizations want to involve more people in the democratic decision making. Also, with the upcoming of DAOs, there's a need for fast and reliable voting platforms. When considering e-voting systems, they have a lot of favorable benefits for voters and organizers in comparison to classical paper-based votings. For example, they are more cost efficient, they provide more security and accuracy, and are better scalable. But they also have some downsides. For example, for voters, it's difficult to verify the correct operation of e-voting schemes because voters have less insight into those systems. So the voter has to put trust in the system and also put trust in the voting organizer to work correctly. This trust requirement is an issue which may be solvable by using the blockchain. The blockchain became popular in 2009 with the release of Bitcoin and the promise of a decentralized immutable ledger, which is resistant against forging and manipulation. Further, the open source approach and the absence of superior controlling entities strengthens the trustworthiness of the system. But today's blockchain are not only decentralized databases, instead they are highly flexible decentralized computing platforms which offer a lot of beneficial properties. And all of those properties makes them a good foundation for voting systems. There are a few blockchain-based voting systems available. Some of them use the permissionless blockchain, which means a user can fully join or leave the system or contribute with their computing power. Others use permissioned blockchains, which means there's an entity that limits the access to the blockchain. Some solutions are suitable for both of them. For our system, we focus on these three properties. We have trustlessness, which means participants are not required to put their trust in the honest behavior of the voting organizers. We have censorship-resilience, which means that no minority of voting organizers is able to influence the outcome. And the system should be scalable, which means adjustable to even a huge number of voters. The way we achieve those properties is decentralization. So instead of a single organizer, which is solely responsible for the important phases of the voting, our eligibility check, ballot opening or tallying, for example, there's a consortium of organizers which has to work together in order to fulfill those tasks. So instead of the voter has to put their trust in a single organizer, the trust is shared between multiple organizers. To build such a decentralized system, we need a few building blocks, which are multi-authority attribute-based encryption, which is used mainly for ballot privacy. We have threshold-blind signatures, which ensures the voter eligibility. And we have the blockchain as manipulation resistant and immutable storage. In our case, it's a permissioned blockchain. So I will briefly explain how or what these primitives are and how they are used within the system. So we have attribute-based encryption, which was introduced by Zahe and Waters as an application of functional encryption. The trick here is there exists a policy which is encoded into the ciphertext. On the other side, there are attribute vectors which are encoded into the decryption keys. And a decryption of the ciphertext is only possible if attributes matches the policy. So for our system, we choose the scheme of Michalewski and Joyce because it was the only scheme, only multi-authority scheme that provides a succinct level of security, and at the same time is also fast because the decryption speed doesn't scale with the number of authorities. Another favorable property is that it supports threshold policies. One have to note here that policy and attribute set are represented as vectors, and the decryption is possible if the dot product of x and y, here the policy vector and attribute vector, equals 0. So how to use this scheme in the context of voting? Suppose there are 3 authorities, which each of them calls the authority setup algorithm in order to obtain a pair of public and private key. While the public keys are published, for example, by storing them into the blockchain, the private keys are kept secret. So now the voter which has access to public keys is able to encrypt the message, for example the ballot, with the help of the public keys. Here X represents the policy, which could be a threshold policy, which means that in order to decrypt, not decryption keys of all authorities are necessary, instead only a threshold of them. So the ciphertext is also stored in the blockchain together with all other ballots, and now after the voting finished, the authority calls the keygen algorithm in order to obtain decryption keys. Here the secret key of either authority is used together with public keys and the attribute vector, which represents the attribute set used to fulfill the policy. Decryption keys are also stored in the blockchain, and finally, with all decryption keys together, a decryption of the message of the encrypted ballots is possible. So next we have threshold blind signatures, which are a combination of blind signatures and threshold signatures. The idea here is that there exists a user which interacts with a threshold T of n signers, and at the end of the protocol interaction, the user obtains a signature of a chosen message, while the signer learn nothing about the signed message. So again, we choose the scheme for our prototype here, and it's the scheme of Kochata and Malouis. I will explain how this scheme can be used. The idea here is that signer engage in the distributed key generation protocol, and each signer obtains a secret key and the common public verification key. The verification key is stored in the blockchain, and now a voter is able to interact with a threshold set of signers in order to obtain a signature, for example over the ballot, and the signer learned nothing about the encrypted message. With message and signature together, signature can now be verified by the verification algorithm using the public key and the message. So next we have the permissioned blockchain. For our system we used Hyperledger Fabric because it's a fast and reliable open source blockchain. In addition, it supports Turing-complete programming languages for creating smart contracts, so the voting program, and it supports or it follows a modular architecture which supports the easily switch in or out different consensus mechanisms. One point to note here is that at the current time, Hyperledger Fabric doesn't support BFT-based ordering services, but they are planned for a future release. In Hyperledger Fabric we have the following components. There are peers, which store the database and execute the smart contracts. We have ordering nodes, which are responsible for message ordering and the block creation. And we have users which interact with both of them. Note with Hyperledger Fabric we are in a permissioned blockchain setting. This means in order to interact with the blockchain, every component has to obtain a digital certificate from an organization. The organization here are superior entities where every component belongs to. So next we have the voting specific components. There are the voters, obviously, that wants to participate in the democratic decision making. We have registrars, which schedules new votings. We have key authorities, which manages the cryptographic material for ballot encryption and decryption. And we have signer authorities, which are responsible for signing the ballots of the voters. One point to note here is that, like already mentioned, we are in the permission settings, and every request sent to, for example, network peer in order to invoke chain code have to be signed. This is a problem with voters submitting their ballots to the blockchain, because if a voter submits its ballot together with the signature to the blockchain, and later in the voting all ballots are decrypted within the blockchain, this is a connection between voter and its choice. So there exists an additional certificate and public key pair, which can be used for signing, which is shared between all voters. It's commonly known and stored within the blockchain beforehand. So by using this shared identity to submit ballots, the real origin of the voter can be disguised. So next we have the protocol phase, or an overview of the protocol phases. Here we start with the setup, which is basically the setup of Hyperledger Fabric components. In addition, signer authorities are prepared. Next we have the pre-voting phase, where a registrar schedules a new voting, and responsible key authorities generate new keys, which are required to encrypt the ballots later on. In the voting phase, a voter encrypts the ballot and obtains a signature from the signer authorities. And finally, there is the tallying, in which key authorities send decryption keys to the blockchain. Tallying is then carried out and the result can be published. So a little bit more detail about these steps. The initialization of the Hyperledger Fabric components. Here, for example, we have 3 organizations. Each of them contributes peers and orderers or ordering nodes to the system. Cryptographic material is generated and digital signatures from organizations are issued. It is important that each organization contributes with peers and later on also with other voting components to the system in order to prevent that a single organization is too powerful and solely responsible for a single task. So after the voting smart contract is deployed on peers and the common configuration was created, which is necessary to boot the peers, the system is basically ready. Now the additional voting specific components have to be added. So sign authorities, key authorities, registers and votings are, like already mentioned, users in the context of Hyperledger Fabric, which means each of them also needs cryptographic material for signing the request, which they send to the blockchain, and they need a digital certificate from an organization, which marks them as member of this organization. So after each of them has the required material, the shared anonymous identity has also been created. As this is a public identity and its purpose is only for ballot submissions, the identity can be stored within the blockchain. Note here that also all content in the blockchain is known by every party here. So next, the preparation of sign authorities, which means the sign authorities execute the distributed key generation protocol of the threshold blind signature scheme. So each sign authority obtains the personal secret key, which is required for signing, and the public verification key. The public verification key is then stored within the blockchain. Now we are in the pre-voting phase. The registrar schedules a new voting within the system. This is simply be done by sending a signed request containing information like title, expiration date, choices, but also the responsible key authorities and the list of eligible voters. Next, for the new scheduled voting, key authorities have to authorize it, which means each key authority which is responsible generates a new key pair using the multi-authority functional encryption scheme. The public key is stored in the blockchain. The public key is required for ballot encryption. So after the voting description is completed, a voter is able to fetch it from the blockchain and use the public key to encrypt the ballot containing the voter's choice. But before the voter is able to submit the ballot, it has to obtain a signature from the sign authorities. Therefore, the voter engages in the signing protocol together with the sign authorities, while the voter obtains a signature and the sign authorities learns nothing about the message. In this case, the message is the encrypted ballot. It is important here that signer authorities keep track of already issued signatures, because it should not be possible for a voter to obtain more than one signature, and therefore vote more than once. So with encrypted ballot and signature, the voter submits both of them to the blockchain. Here, it is important that the voter uses the anonymous shared identity, which disguises the real origin of the voter. After this is done, the tallying phase, key authorities have to unlock the ballots, which means key authorities use the key generation algorithm to obtain decryption keys. Decryption keys are stored within the blockchain. And with decryption keys now together in the blockchain with all the ballots, the voting can be finalized. Therefore, the registrar triggers the decryption process of the smart contract, and the decryption can take place in the smart contracts of every peer. So one can say that the system achieves most of the important e-voting properties, and this Hyperledger is basically a good choice for such a system due to its flexibility. With the addition of multiple more peers, the system can be scaled. Well. Also, steps that remain is the completion of the system and performance analysis using the BFT-based order once it's available. Also, formal security analysis is still pending. Thank you.